I'm going to watch this video when you're just 7 years old.
The rest of us are here too.
So anyway. Welcome to class. Today we're going to talk about inverse trig functions. We're going to take the derivatives. So if you look at our scale checker today, I can have the derivative of an inverse trig function. How many people remember everything there is to know about inverse trig functions? No.
Yeah, well,
Just Foster. He's the only one that remembers everything. So, Devin Wood. Shout out there. All right.
Rusty would do.
Russell, okay. Shout out. Oh, okay.
And Rustin.
Maggie wants in.
There's
All right.
here.
So, what I'm going to do is review you on the basic stuff about where the inverse trig functions come from, just to kind of refresh your brain. You don't necessarily have to write everything down on this. You're more than welcome to write anything down that you want, of course. PowerPoint is in your stream, and when I would more need you to write stuff down will be pointed out, and then also when I actually start taking derivatives. So I'm just trying to get your brain going here. Okay, so when you talk about sine function, so you know the basic shape. What's the period of sine? 2 pi. Go 0, 1, 0, negative 1. Okay, but is it a function? Is sine a function? How do you tell if its inverse is a function?
Plug it into the
Vertical line test, but the
horizontal
line test, which is kind of already on there. If you put a horizontal line through and it touches more than one point, then its inverse would be a function. Well, we know there is an inverse trig function. What they did was they limited the domain so that it would pass the horizontal line test. So what they restricted it to was just from negative pi over 2 to pi over 2. If you just look at the red portion of the graph, would it pass the horizontal line test?
Yes.
Yeah, it would. So that's what they did, and that's so that they could get a one more answer. So when you do inverse sine on your calculator, you get one answer. And it's based on this. It's only going to give you an answer between negative pi over 2 and pi over 2. When in fact there are more answers. Okay, and that's why we do the plus 2 pi n, if you remember. But because there's, every time you go around the circle, there's another answer. Okay, so for example, if I said, what is the angle whose sine is 1/2? Can you see anything on the unit circle that has a sine of 1/2? Give it to me. 5 over 6. Okay. Is that the only one? Or is it other one? You kind of have to use your imagination to put your points on something, but where would it be logically? 5, 5 or 6 would be right here. This is also at a height of 1/2. Now your calculator is not going to give you two answers. If you say the inverse sine of 1/2, it's going to give you, depending on what mode you're in, it's either going to give you 30 degrees or it's going to give you pi over 6 as a decimal. And so that's so that we have 1 to 1. So if I ask you the angle whose sine is 1/2, the calculator is going to tell you 30 degrees or pi over 6. Okay, so they restricted it so you get one answer. It doesn't make it not true that the sine of 150 degrees or 5 pi over 6 is 1/2. Okay, but they restrict it so that the inverse trig function gives you one answer. You can logic your way around to get more answers. Okay. So this is the inverse trig function. If you graph it, let's just off your Inspire calculator, a screenshot of it. So if you look at it, and actually let me go back one slide. So if you look, we limited the domain to be between negative pi over 2 and pi over 2. What's the range?
Negative 1 to 1.
Negative 1 to 1. And so when you do an inverse function, you switch the domain in the range. Okay, so what's my domain going to be for inverse sine? And my range? Okay, and so that's what you're seeing on this, okay, as far as the domain and the range. See how it looks like it's going from negative 1 to 1, and this would be negative half pi to positive half pi. Okay. And actually, we just did that example. That's the answer up there. But the angle whose sine is 1/2, we looked at the unit circle and said, hey, there's two spots that have a y value of 1/2, pi over 6 and 5 pi over 6, but it's going to give you the one that's between negative pi over 2 and pi over 2. It asked you the angle whose sine is square root of 3 over 2. Okay, and it told you the answer, pi over 3, but is there another answer on the unit circle? sine of square root of 3 over 2. So we already know this one. I know, we gotta figure it out.
60 degrees.
Okay, so this is 60 degrees, but where else? Yeah, 2 pi. Okay, so right here, I don't know what, yeah. And so there's 2 that have that, but again, if it's inverse trig, you're only looking between, inverse sine between negative pi over 2 and pi over 2. So let's talk about what a negative one would look like. So let's do, what if they asked you the inverse sine of negative 1/2? Now, I don't have all the values filled in, so you have to figure out where negative 1/2 would be. What angle do you think that would be? Okay. So I don't disagree. That would have a y value of negative 1/2, and this is square root of 3 over 2. Okay, is there another spot? Okay, this would be over square root of 3 over 2 and down 1/2. However, so you told me 7 pi over 6 and 11 pi over 6 both have a sine of negative 1/2. However, your answer that you gave me is supposed to be between negative pi over 2 and pi over 2. So what could you tell me if I wanted an answer between negative pi over 2 and pi over 2? That's it, negative pi over 6. So in that case, you just have to look at it in these 2 quadrants, but consider these to be negative angles. So this would be negative pi over 6. And that the only purpose for that is to get a 1-to-1 answer. So then if you do it, and so if you do this on your calculator, inverse sine of negative 1/2, if you're in degree mode, you'll get negative 30. If you're in radian mode, then you'll get whatever pi over 6 is as a decimal. All right, inverse cosine is the same way. It would fail the horizontal line test, so they decided to restrict its domain. They picked from 0 to pi. Now, they couldn't pick from negative pi over 2 to pi over 2 because it would still fail. Okay, but that's the one thing that kind of irritates me the most, because I'd kind of like them all to have been limited in the same way. It's just a personal irritation. So, like, if I go back to sine for just a second, could they have done 0 to pi? Would it have failed or passed the horizontal line test? Failed. Okay, because it would have crossed right here and right here. Could they have picked a different interval? Could they have picked pi over 2 to 3 pi over 2? Okay, so it was kind of, whatever they decided. I don't know when they decided, but that's what they decided. But it's kind of irritating to me. Yes?
It's not kind of vague, like why exactly the horizontal line test pretty vague?
Because it's the same way as vertical line tests, because you're trying to show that it's a function. That's what you're trying to do. So for vertical line test, you're saying for every x, there's only one line. And so if you flip it, and you have...
Oh, okay.
Because I might have gotten tongue twisted weird. Sometimes I have to draw it out. Okay, so cosine, like I said, they restricted. And so they did from 0 to pi. And so when you do inverse cosine, you're actually supposed to look at the answers from 0 to pi. Okay, so I sometimes forget which one I'm supposed to look where. So I have a slide that just reminds you where to look, and I'll tell you to write that down when we get to that slide. But so for inverse cosine, you should only look for your answers between 0 and pi. Sorry, I was just going to look at the domain and range again. So the domain of this, they're saying, is from 0 to pi. We're restricting it. And then the range is still negative 1 to 1. So when you do the inverse, those just flip-flop. And it's probably going to tell me the answer. Oh, shoot. It is telling me the answer too fast. Okay, so let's just pick one. So we know that it has to be, cosine is just the stuff we're going to look for arc cosine. We're just going to look between 0 and pi. So let me just pick a random. We'll do one. Arc cosine of, let's go for, what do I have here? I already have that, so let's do negative square root of 3 over 2. Okay, so what are you looking for on the unit circle? And I realize some of them aren't fully filled in, but x value to be negative square root of 3 over 2. What quadrants could that possibly be in?
Second, third.
Second, third. Good. What quadrant am I supposed to look in for on cosine? First and second, so I'm going to have to look in the second. Okay, Okay, so arc cosine of negative square root of 3 over 2, what do you think? 5 or 6, good. Or 150 degrees. Okay, and that one's over the farthest. It's over the distant horizontal distance of square root of 3 over 2. Okay, so that just kind of tells you where you're supposed to look. Okay, so inverse tangent, here's tangent, same problem with tangent, fails the horizontal line test. And before I hit it, do you know where they restricted? I think it's going to tell me before I click it. Yep, so they just took one nice swoop of it. So your asymptotes are at negative pi over 2. Pi over 2 is the period of tangent. What is it? Pi. It's repeating every pi. So the distance between asymptotes is the distance of pi, negative pi over 2 to pi over 2. It's repeating the same pattern every pi. So that's where they restricted it. This is what inverse tan looks like. You need to know what inverse tan looks like. This will come up like 5 billion times next year. Okay? So arc tan of x, or you can write tan inverse x, it doesn't matter. I'm just drawing the same thing that it says here. But you need to know it has an asymptote at pi over 2 and negative pi over 2. And I'm just literally drawing the same thing it says right there. But you need to know that graph. So you don't particularly need to know what arc sine looks like or what arc cosine looks like. You know how to calculate it. But arc tan, it's going to come up this very common limit that they want us to know. It's going to be in the middle of improper integrals and all this kind of stuff. Improper integrals, well, I haven't even told you what integrals are yet, but it's the opposite of derivatives. And they're going to have bounds that instead of being numbers are infinity. And it's going to require us to take limits as you go to infinity. And so this is going to be a question they're going to want you to know. And they will want you to know the limit as x approaches infinity of tan inverse of x. Okay, so what you're doing, remember, this is telling you what's happening to the x values. The answer is what's happening to the y values. So if you look at this function, as you go towards the end behavior of the function, what's happening to the y values? What are they heading towards? Pi over 2. And they're going to expect you to know that. That's like one of their favorites. You're just going to have to trust me. It's going to come up in the middle of some other convoluted situation. Okay? Okay, so what would be the domain of this problem? All our numbers and the range. Okay, so when you flip back to the tangent, what we just said for the range was the restricted domain, negative pi over 2, pi over 2. And the range of tangent was all real numbers, remember, because the tangent looked like a little squiggle like this. So we restricted the domain to be from negative pi over 2 to pi over 2. And the range, though, was as low and as high as you wanted. Okay, so that's where we would look for tangent. I think that's maybe what you were more asking me, is where would I look if I was doing an inverse tangent problem between negative pi over 2 and pi over 2. The other thing they're going to want you to know is the limit as x approaches negative infinity. What do you think about that? Negative pi over 2. Okay, so that's just what this function does. As x goes towards negative infinity, the y value is flattened out. Okay, so that's just going to be something that comes up next year. It just needs to be, you don't even need it for this lesson. It's just something that's going to come up next year. So I erase this, that's all right. We got here. Oh, there you go. There's the domain and the range. It's a little bit harder to do your inverse tan problems because you have to do sine and cosine, so it's really, really annoying. So we want to look just between negative pi over 2 and pi over 2. So an example might be, well, they've got some. They've got the inverse tangent of square root of 3 over 3. So if you were trying to figure that out, I realize the answer's up there, but you be thinking, which one will the sine over cosine, if I do it, come out to be square root of 3? And so, we've got cosine, we've got sine, and you wanted it to come out the square root of 3 in the numerator. So, well, here's the thing, they rationalized it. Anyhow, so if you do sine over cosine, you would do a half divided by square root of 3 over 2. So that'd be a half times 2 over square root of 3, which would be 1 over square root of 3, which if you rationalize it, is square root of 3. Okay, so the tangents are more of a problem because you have to actually sit there and divide. You would know that it's got to be one of the ones with square root of 3, isn't it? So you basically have to test between these two. The fact that they rationalize it kind of throws you off a little bit, because otherwise you figure the square root of 3 would be able to make it. Okay, so that's where you look for those. You don't really need this slide. You can graph it. Okay, so if you forget, so on your calculator, if you hit the trig button, then you'll see you can hit the inverse sign, and that's the same. When they write to the -1, they don't mean 1 over sign. You have to know that means inverse. Okay, so they don't mean 1 over sign, even though if they wrote sine x all raised to the -1, you would think that. So you can graph it on your calculator, remind yourself. Yes, you want to graph in radian mode. Otherwise, you just have to make your domain so much larger, because instead of like, if you think about going from -2 pi to 2 pi, you'd have to be going maybe 360 to 360 if you change it to degrees. Okay, everything you do in calculus, you want to be in radian mode. Who can tell? Always. This is in radian mode. The derivatives are based on that. Now, could you, like the derivative side isn't cosine anymore if you're not in radian mode. You have to take care of the factor of changing from radians to degrees. Now, if, however, you're wondering, you know, the angle whose sine is a half and you wanted to tell you in degrees and you change it to radians, I mean, that's different. But as far as your answers in calculus, you have to use radians. Why, when they put in arc sine of 2.5, did they get an error? Because what can sine be? What's the lowest and highest it can go? -1 to 1, the original function. Okay, so if you say, give me the angle whose sine is 2.5, there's not one. So also, this isn't in the domain of the problem, but it's not in the range of the sine function. Okay. So some of this, like I said, I'm just going to go through fast because it's... basically speaking, you have to remember their inverse. So if an inverse undoes the work of the regular problem, so if you substitute the inverse of the original function to the inverse, you get back to what you started with. So if I ask you, what is the sine of arc sine of x? I'm saying, what's the sine of the angle whose sine is x? Well, it says, what's the sine of the angle whose sine is x? It's x. So sine and arc sine undo each other, cosine and arc cosine, tangent and arc tangent. You do have to be careful about the domain and the range, that you're putting numbers in that are appropriate for the situation. If you're not in the correct domain and range, then it doesn't work. Most of the time, they're not going to try to show you them. I opened the blinds. Flashlight. You can stand up. There's like a whole back of standing up. They'll scoot for you. Ethan's so agreeable. He like always tries to help people. He's like, doesn't think of his own needs. He's like, how can I help others? He does what? Yeah, he does walls.
I scoot over with people.
Okay, we'll see. There you go. All right.
She's like always kind of in the middle of the room, like right in front of the room.
Okay, I paid to get rent and then you forgot about it.
We'll
That's
remind
just
him.
good capital.
Yeah, we're reminding him on the video.
Hey Keegan, don't forget you need rent for your spot back in the room. And he has to watch the video, so we'll see.
But will
Yeah, so we have a test.
Okay.
Okay.
You should put like a code word in there, and then if they watch the video, you should be like, "What's the code word?"
Okay, what's the code word?
I think this is
Banana.
naval block.
I think it should be flashlight because you like told
Austin
Tara.
picks the.
That's Aiden.
Aiden picks the. Aiden picks the word. Code word. He's gonna think of it. He'll let us know. Yes. Yes.
Oh.
Oh, we
I
need a
thought it was
code
more
word.
like teacher thing.
No, my teacher
So
thing, I would need pictures of you. Oh, I already did it, and I thought it was good enough, and I'm not ever doing it again. So I did one 10-minute video, so you will not be videoed.
No, can you show this to other math teachers? I want to give a shout out to my mom.
You think your mom's
Hey,
gonna
Carrie, I
watch
love
it?
you.
Okay, now, I'll post it. You tell her to watch it. Wait for the shout out. Sure, she'll be riveted and excited to see what it's saying.
Yeah.
So apologize.
I mean,
What's the code word?
Gooby.
Gooby? Code word is Gooby. You heard it. All right. So here we go. So this is. She's not gonna remember. Okay. Now this is not an inverse function. This is secant. Okay. So I'm reminding you about the other trig functions. There are inverse trig functions. You don't have to really know anything about the inverse trig functions of the reciprocal functions, because anything you can do, anything you can do with the reciprocal functions of sine, cosine, and tangent, you could have done with sine, cosine, and tangent anyways. It's just not something that really comes up. But I would like you to know how to form it. Can you see this tiny green line? What is that tiny green line?
That looks like so.
Oh, which one is it?
Ah.
There we go.
Okay, that's cosine. Secant is the reciprocal of cosine. Okay? So what you see here is they've graphed cosine. Okay? And so if you look at the spots where cosine is 0, what is this spot, by the way? They didn't label it very nicely. Pi over 2. Okay? So pi over 2, at pi over 2, you would get that cosine is equal to 0. So what happens is 1 over 0, that's where you create your asymptotes. So any place that cosine is equal to 0, secant has an asymptote. Okay, now what's the value of cosine here? 1. What did you get when you flip 1? 1, so that's why this point matches. Okay, but then maybe right about here it's a half. Well, what do you get when you flip a half? 2, so it's going to go up to here. And then maybe this is like 1/10 or something. Well, that's going to be 2. So what happens is it gets teeny tiny here. When you flip it, it gets super huge. So 1 over super tiny is super huge. Yeah.
So this is sophisticated.
Fancy stuff, right? Well, it doesn't look sophisticated after I drew my pitiful lines all over it, but it looked pretty to start with. Okay, you can also do, that's what inverse secant looks like. I don't care what it looks like, but I'm just trying to remind you of, these are called the reciprocal functions. Okay, it's just good for your brain. Is that, yeah. So when you're seniors and you're getting ready for your final exam at Christmas, you won't like me as much because I'm going to review pre-cal stuff and all kinds of stuff that's going to be on your final. Pre-cal and calculus, just because I'll be like trying to get you to remember everything that'll be on the HL test. Yeah, it won't be as nice as your curve station test.
How long is the HL test?
5 hours. So paper 1 is 2 hours, paper 2 is 2 hours, and paper 3 is 1 hour.
I thought you were kidding.
I'm really kidding.
That's a lot.
Just 9.
You have all your other subjects too.
Well, I only have one more.
Oh, well, there you go. What's your other one? Oh, you picked like the 2 hardest ones that exist. So, yeah. And then
And I have lifetime physics.
it might be. I think chemistry might be harder than physics. Okay.
Easier grade water class.
Easier
You get
grade.
your analysis compared, and then your brain will.
Well, sometimes he curves. No, he does sometimes. When it gets bad enough, it's like me. I'm not curving anything for you. It hasn't got bad enough. And I do test corrections if it's bad enough, which it hasn't.
What do you do?
It's gotten
Just
bad.
like
Not first. No, because I know what you should be able to do, what you shouldn't be able to do. So if you bombed something already, I wouldn't have done it. It's just when the material gets super, super tough, sometimes I'll throw the seniors.
So like bad enough, like the highest.
Their last test, they have those corrections. They just had this. It was a tough one. Okay, so this is cotangent. And so, whoops, sorry, I went too fast. So cotangent is the reciprocal of tangent. Did I not give you a cosecant? Maybe it's next. Okay, so there's cotangent. It's 1 over tangent. So any place that tangent was 0, this has vertical asymptotes. So if you remember tangent, make sure I'm on pen. Tangent had negative pi over 2 and pi over 2. It was 0 right in the middle. Okay, so 1 over tangent, that says 1 over tangent x. Wherever this is 0, it's supposed to be 1 over tangent x. Use your imagination.
I am.
Okay, so where this is 0, this has a vertical asymptote. Okay, so that's cotangent. And for some reason I didn't give you whatever I missed, cosecant. Do the same thing with sine. I don't know why I left it out. This I would write down. Write this down. Okay, so this is just telling you if they do the angle whose sine is whatever, like arc sine of 1/2, it's telling you where to look. Okay, so for sine and tangent, arc sine and arc tangent, you're going to look between negative pi over 2 and pi over 2. But for cosine, you're going to look between 0 and pi. Yes.
How do you spell trig?
Like it says right there.
No, not that. Like trigonometry.
It's on my board.
Just change the ick to a Y.
No, okay, but there's a.
Yeah, why is it
On the other side.
trigonometry? Why is it trigonometric?
Trigonometric?
Is it
I don't know.
trigonometry?
Wait,
Is
it trigonometry?
It is trigonometry. It is not trigonometry.
Let's just confuse it.
I don't know.
Someone
I
analyze
mean, it's
that.
not like anybody with down is going to watch it. I hope that's
Should we all go around
No,
and
Emily.
compliment Devin? Can we? That would be so nice.
I mean, they might be hearing you right now. I don't
Happy Hanukkah. I have to film every day, twice a day. Once a night, once a mystery.
Wait, when is it? Did it start at the beginning of the month?
No, it started
It started the.
When's it at?
When did it start today?
My days are 7,
Did it start today?
8, maybe 7 or 8.
It started yesterday.
Are you ready?
No.
When you see range, do you look on the next circle for that?
Yes. So for if they said arc sine of 1/2, I'm going to look between negative pi over 2 and pi over 2 on the unit circle for something that has a sine of 1/2.
But how do you know it would be that side?
Well, this is so this is 0, so this would be 0 to pi over 2. Negative angles start here and go backwards. So that's negative pi over 2. This is 0. So going counterclockwise are your positive angles, and clockwise are your negative angles from this side. Okay, are we good? Can we go on? Not go on.
I got two ranges.
The range is the super big deal part of it that I want you to try and remember. Honestly, I pulled up the slide and made sure you two designs.
Oh, just do it.
The answer. So,
So, are all domain and range going to be the same as the So, arc sine and set is the same thing as cosine?
yes, how far? So, like sine is normally between negative 1 and 1. So that's the range of sine.
So it's like you could like set arc sine and arc cosine.
No, let's just switch the domain and range.
Oh, there's that.
Yes. Okay, now we good? I hope so. Okay, so this is going to be kind of what's going to lead you into doing the actual derivatives of these arc functions. So like the derivative of arc sine, the derivative of arc cosine, the derivative of arc tan, that's what we're doing today. So in order to do that, I have to help you with this problem. So this says find the exact value of the tangent of the angle whose cosine is 2/3. Okay? And the way we're going to figure that out is we're going to draw a triangle. I already have a nice triangle on the board. Okay? And so when you look at this part, okay, this right here means the angle whose cosine is 2/3. Arc cosine 2/3. Tell me the angle whose cosine is 2/3. This is not a unit circle value. You cannot look on here and find 2/3. Okay? I mean, you can know like what it's going to be to try to get how high is 2/3 and go over, but you're not going to get an exact unit circle value. So what you're going to do is you're going to let you want u or theta or what?
Theta.
V. U or theta or what? Should be positive or negative?
Negative max.
No. We're not going to make it negative.
It's all, no,
not
no,
negative.
it's not negative. It's in closing the parentheses, so it really
No.
has no for me
No.
being negative. I just like it. On X triple prime.
Yeah, I'm a passer on that.
What are we going to use for a variable? Theta.
Oh.
What a logical choice. Not triple prime. That means the third derivative. Why would you do that? It means something else.
It
Why
means
would
something
you
else
use
in a
Greek
different
when
type
we're
of.
speaking American?
It's math. We speak Greek. We don't speak American. What are you talking about? All right. So here's theta. So this is theta. The angle whose cosine is 2/3. Okay? Cosine is a ratio of what? Two sides.
It's the right button.
Sorry, it looks terrible. So the angle whose cosine is 2/3, I'm going to draw this angle so its cosine is 2/3. So its adjacent will be 2, its hypotenuse will be 3. Okay, so adjacent and hypotenuse. Okay. What I'm going to do now is solve for the unknown side. The reason I'm going to solve for the unknown side is now it wants me to find the tangent of theta. Tangent is opposite over adjacent, and I don't have the opposite. So, yeah, let's just do Pythagorean theorem. So 2 squared plus b squared equals 3 squared. Square root of 5. Now technically it's plus or minus the square root of 5, but clearly I want the positive.
We're above the X.
We're above the x-axis, that's a positive square root of 5. Okay? Yes.
Is that one of the things that you can just memorize, like the triple?
Pythagorean, that is not a Pythagorean triple because Pythagorean triple is like when they're all whole numbers. And they try to get you to memorize those so you don't have to stop and go back. Okay.
Are we going to be ones with like,
That's
about
the fact.
2/3 exactly?
Um,
That's interesting.
right. Not from this one. Everything we're going to do is going to be positive.
Okay.
We could though. It's on ingenuity. Let me finish this one. Okay. So now you drew theta, so it was the angle whose cosine is 2/3. So now this is just tangent of theta, and the tangent of theta would be what? Square root of 5 over 2. Okay, opposite over adjacent. Okay. So I was asked the question, what would we do if we got like a negative value? Okay. They have to tell me a little bit more because cosine could be negative in this quadrant or this quadrant. Okay, so I would have to know something else in order to determine what. Like if I knew if tangent was positive or negative, that would help me. So actually, this wouldn't be enough information to figure it out. If that makes sense. So if you gave me an ingenuity problem, I could do it. It's kind of hard to. I can't remember what. They have to give you 2 pieces of information because you have to know both if the cosine is positive or negative and if the tangent is positive or negative to decide which quadrant. Otherwise, you have 2 choices. Yeah. Right. We didn't find theta. Never found it. If I wanted to find theta, I could do it in the calculator. Arc cosine of 2/3 and get it in radians or degrees. But no, we didn't find theta. We just found the tangent of theta. Okay, so that leads me into what I'm actually supposed to teach you today. Okay, that was just like a little refresher. Yeah, it's just a little 34-second refresher. And so it's just, still recording. We should be. Yep.
It's like when you take a really long nap, and you're like, wow, that was supposed to be refreshing, but I just feel worse.
Thanks.
Except the nap was
Yes.
I'm really.
Yes.
Would you say as an American citizen that the United States is better or that Russia is better? One word answer.
Do not answer. This could be nuclear weapons.
And you're being recorded.
Point taken. So here we go. So notice I have to tell myself stuff. Do this after the PowerPoint. When you get old, you have to put like reminders up for yourself, different things. So this says write the expression in algebraic form. So still I'm not taking derivatives. What I'm doing is training you how to work with the functions. So this says find the secant of the angle whose tangent is 4x. Okay? So find the secant of the angle whose tangent is 4x. I don't care what like the actual angle is. So what you're going to do is you're going to draw an angle. Okay? So we got to name this angle theta. Theta is going to be the angle whose tangent is 4x. Okay? And so tangent is a ratio of what?
Does this only work for right triangle? Or are we just doing it?
I mean, this is right. I am doing right triangle trig.
So we're assuming that all the triangles we're working with are right?
Yes.
Okay.
Because the ratio, if we're going to say, if we're going to use the terms opposite and adjacent and hypotenuse, it's implying, even hypotenuse is implying that when you use the ratios in that way, that you're dealing with a right triangle. Good question. Like how he sneaks in like he's on film. Okay. So tangent is a ratio of which two sides? Opposite over adjacent. So I'm going to make this, and this doesn't look like a fraction, so I'm going to put it over 1. So the angle whose tangent is 4x, or 4x over 1, so basically this is your 4x, and this is your 1. So the opposite is 4x, the adjacent is 1. So that's that angle now. The angle whose tangent is 4x, gave it a nice little name, that's theta. Now I want the secant of that angle. Now I can't think of what the secant is, but what's the reciprocal of secant? Do you know? Okay, so let's just write real quick. We got sine, cosine, and tangent. Those are our typical ones, right? Those are our 3 primary. What are the ratios of sides? Okay, so for me, nobody ever agrees with this, but for me it's some old horse came out hopping through our alley.
Sokotoa.
I don't know why
There's a
anyone
story.
would
There's a
like
story.
Sokotoa, but here's the thing, you have to learn how to spell Sokotoa to remember.
It's literally like she's saying a word.
You have to remember all of them.
But it doesn't look like Sokotoa.
It's pronunciation.
Yes, it does. It looks like Sokotoa.
To me, it was harder to remember how to spell
What did
Sokotoa.
you say?
Actually, I didn't. Some old horse came a hopping through our alley.
No, it's some old hippie caught another hippie tricking on this.
Oh yeah, that's it. But again, am I going to say that? But the other thing is, we didn't have any of those back in the dark ages.
Story.
So I would remember.
Say it?
No. Thanks. No, because then you're going to put it on clip. So anyway.
I didn't record it.
Anyways, I used to remember, because I didn't have any of those cutesy things to remember. Sin was the opposite of what you're supposed to do. So I would be like, because all I had trouble remembering was which one was opposite, which one was adjacent, because they're both over hypotenuse. So I was like, sin's the opposite of what you're supposed to do. And so then I could remember cosine was the adjacent one. And then tangent is sine over cosine, so if I really had to, I could figure it out.
Or a
I didn't have Sokotoa. Nobody thought of it. Didn't have some old horse. I think I got that from this crowd. So, and then anything with drugs is not going to be how I'm going to remember math. So, okay. Now, no. That's how you remember it. It's not how I remember it. Reciprocal functions, you're going to, the S goes with the C. Cosecant, sorry, that's CSC. And then this one's secant, and this one's cotangent. So these are the reciprocal functions. So that just means I can flip all these guys. And I actually have to write I don't have to write all the reciprocal functions, but like for me to do secant, I have to think of cosine first and flip it, and that's just how my brain works, because I learned these 3 first. Okay? And so that means that if I'm going to do secant, I need hypotenuse over adjacent, and I don't have hypotenuse, so I need to Pythag to figure out the hypotenuse. Okay, so here we go. I don't know where we want to do this. 1 squared plus 4x quantity squared equals c squared. So you'd have 1 plus 16x squared is c squared So when you take the square root, it is the square root of 1 plus 16x squared. Can you take the square root of each part of that separately? No! Square root of 1 plus 16x squared. Can you take the square root of 1 and square root of 16x squared separately?
Yes.
No!
No. That's
Okay.
gonna be a quote.
I'm pretty sure we've had this conversation multiple times. So if you have the square root of 1 plus 4, what is the square root of 1 plus 4? Square root of 5. Okay, if I take the square root separately, I would have 1 times or plus, I don't know what you're going to put, but you're not going to get square root of 5.
But you can take it separately if they're multiplied.
Yeah, if they're multiplied, that's fine. Times. Okay? Or 104, one or the other. But I mean, the square root of 4 is 2. And if you do it separately, it works too. But only if it's times, okay? Not if it's plus. Please don't do that to me. I've told you 50 times. Not 50, but like 2. All right, so now we can do the secant. The secant is hypotenuse over adjacent. So the answer to this problem, I don't know where I'm going to put it. I used up all my room. Perfect spot to put it. The answer to the problem, what do you think?
Is 1 square root of 1 plus 16x squared over 4x.
There's only one other choice. Hypotenuse over adjacent, so over 1. So it's just this. So that is the secant of the angle whose tangent is 4x. That was fun. Please find the cosine of the angle whose cotangent is x. Try to draw it, see if you can do it. I'm just going to pause it to try to save myself some recording time.
And then you need to listen
Listen to Caroline.
All right, you're good.
Megan, listen to Caroline.
All right.
Caroline has your question that's important.
Oh, what's the question?
She wants your candy. Is that okay?
Okay. Yeah, Caroline, you can have it. All right.
Oh, she's got the mic.
It's fairies.
So, Rita.
Power.
Do you give your senior HL kids a chance to be on the line?
Yeah.
Really?
Got a piece.
I feel like that backwards sometimes.
Okay, so anyways, she's explaining to us. She's done a theta.
I have done a theta, so arc cotangent of x is like theta, which, yeah, so this is the inverse of tangent, which is adjacent over opposite. So x over 1 means in the beautiful triangle that we have. This would be x and that would be 1.
You switch it over.
Yeah, sorry. Better? Better. Alright. So then you find that, which is plus 1.
This is legendary.
Okay, and then
Yes. I don't know if
We got it over.
Alright, so here we go. Let's see what
Here we
she
go.
did. Besides
All right.
distracting troublemakers in the back, we have math in the front. Shush, shush.
yeah, okay.
That's unfortunate. Okay, so here we go. The angle whose cotangent is x, she's labeled. How did she figure that out? Maybe she'll tell me.
This,
Yeah.
so she did some different work and then realized that it's just the inverse of tangent, which tangent is opposite over adjacent, so cotangent is adjacent over opposite, and since x is not the angle, x is the other value, it's x over 1, so that means the adjacent is x and the opposite is 1, So then you come to my beautiful little triangle here, and you've got x and 1, and then I found the hypotenuse, which is the square root of x squared plus 1, and then cosine is adjacent over hypotenuse, so that's x over the square root of x squared plus 1. Yes.
So it's in ratio, it's just a ratio. Because all these are just ratios of sides. So, okay, same ratio. Beautiful, thank you. Can I have one
Yes.
back?
Please take your mic back.
Okay. Okay, so all of this I have done just to prep you for understanding the proof of the derivative of arcsine. You needed all that knowledge. Okay? All right. Aiden, do we have a second code word or only one?
Do you have another piece of paper, another paper than
Just one. Okay. Does anybody remember what it was?
that?
I wrote it down.
If I do, it's in the back. All right. So here we go. As soon as you see this, y equals sine inverse of x, we're going to draw that triangle. Draw a triangle. Okay? And so here I go. Now, I don't get to pick the letter anymore. Y is the angle whose sine is x. They told me. They didn't say it was theta. They said y is the angle whose sine is x. So this is going to be y. Okay. And then the sine of y is x. It's the angle whose sine is x. So sine is a ratio of what two sides? Okay, so opposite over hypotenuse is x. I'm going to go ahead and solve for the missing side. If you Pythag, what will this missing side be? Okay, I mean like the answer. I agree, it could be A or B, but yes. So I'm just going to say, yeah, well, either way you want. Okay, so let's just put 1 minus x squared. That would be pretty easy. Okay. So now what I'm going to do is, my goal in this, y is the inverse sine of x. My goal is to find y prime. What's the derivative of inverse sine of x? Here's what I'm going to do. I'm going to take the sine of both sides of this equation first. So the sine of y equals the sine of sine inverse of x. I'm taking the sine of both sides. Doesn't that cancel? Is that what you wanted to say? It does. So what would that be? Now I'm going to take the derivative. I'm going to take the derivative implicitly. Now, technically it's solved for one of the variables. It's solved for x. But I do have x's and y's, so I'm going to take the derivative all the way through implicitly with respect to x. So what is the derivative of sine y with respect to x? And then on the right-hand side, 1. Okay, so the derivative of x with respect to x is 1. Okay, now I'm trying to find dy dx, so I'm going to solve for dy dx. So what do I need to do to both sides? Okay, so I've got it, but I can actually figure out what the cosine of y is. Because there's y.
Cosine of y is x.
No, it would be square root of 1 minus x squared.
Cosine is adjacent over hypotenuse, so you'd have that is a lot more ugly. I think I could have used a reciprocal function. It would have been prettier. I could have just said, what's the reciprocal of cosine y, and flipped it to start with. Okay, but it's 1 divided by that, so it would be 1 times the reciprocal. So it is 1 over the square root of 1 minus x squared. So now, whenever you want the inverse sine of x, it's just 1 over the square root of 1 minus x squared. 2 for the exam. these are the three rules associated with the derivative of arc sine x, arc cosine x, and arc tangent x. I just proved the first one. You proved the other two the same way. Just for fun, I did that last night to see how long it would take. It doesn't take very long. If you'd like to prove the other two, we can. If you'd like to skip it, we can.
Skip.
Those are on your formula sheet. I will never remember any of them without looking up the formula sheet. Their favorite one, when we go backwards to inverses, will be the arctan.
Is that a negative?
That is a negative. Okay, so these are on your formula sheet. They are not memorized even in my brain. Okay, they just don't come up all that often. If I need them, I look at the formula sheet. So this one's positive, this one's negative, and this one, I don't know, it's their favorite. When we go backwards and do inverse or integration, their favorite integration is the integral of 1 over 1 plus x squared is arctan x. They like that one going backwards the most. They just kind of overuse it. So that one, when I see it looking in that form, I automatically think of arctan, just because they do it so much. But the others, I look at the formula sheet. So we have these three new rules. I want to show you where the rules came from, so there's all that other stuff. It also, all that other stuff is going to help you when we do integration going backwards. We're just going to apply those rules mixed with every other rule you've already known so far. Okay. So here, when it says arc sine of x squared, that means that I'm using this rule, right? But what am I putting instead of the x? X squared. And then once I substitute that in, what? You gotta do the chain rule times the derivative of the inside function. Okay, so you're using these three rules. And so for the first one, for arc sine x, I'm using this rule. So f prime of x would be 1 over the square root of 1 minus, instead of the x, I put x squared. So right there, instead of that x, I'm putting in x squared, so it's still got to be squared. And then times the derivative of the inside function. So times what? And that's just the answer. So 2x over the square root of 1 minus x to the fourth. That's easier than all the other stuff we did. Okay. To where you could possibly see it, that would be smart. But there's less mystery involved that way. Okay. So, we're going to try a few more. We're going to go to the right. You ready? Ellen, notice this has nothing to do with the lesson, okay? But you already know how to do it. And then this is an arctan, so we figure out how to substitute that in. So this is adding and subtracting. You take the derivative of each term one at a time. Tell me how to take the derivative of ln of x squared plus 4.
1 over x plus 4.
Yes. And then we have minus a half. Now I'm going to use the arctan rule, which I didn't prove. But basically, instead of this x, I'm putting in x over 2. So I would have 1 over 1 plus x over 2 squared. And then I have to say times the derivative of x over 2. What's the derivative of x over 2? 1/2. Now, I can make this much more beautiful. Or not.
No.
So that's the derivative. Okay, can I move to the next one? Okay. So arctan of the square root of x. Wait.
Will our test be after?
Well,
You said our exam was 2 rounds, and like all the things together.
Thank you.
How many more examples do you have?
4.
Wait, why is it?
That's the derivative of x over 2, chain rule, times the derivative of the inside function. Yes. Same thing, slower. Here we go. I'm going to move this so I can see the rule for arctan x. Okay. So we're doing arctan square root of x. So where I have x, I'm going to be putting square root of x. And then times the derivative of square root of x. Okay, so f prime of x. Wait, I have a question. X to the 1/2? Doesn't matter. Well, I say that. That's not true. I'm going to have to write it as x to the 1/2 to do times the derivative of the inside function. So you can do it now or later. He's thinking ahead of me. He's faster than me today. All right, so here we go. 1 over 1 plus, that doesn't matter here. I can put square root of x squared. Well, yeah, that's x. I thought you meant after that, like plus x. I was like, no. Okay, and now, okay, so Michael's exactly right. This is x to the 1/2. So when I say times the derivative of the inside function, I kind of need it to look like a power. So what's the derivative of the inside function? Uh-huh. That's the derivative. You can make it slightly prettier, but you can make the last one way prettier, but that's okay.
So are you required to solve down?
No. It's just if you need it to find something else.
To make it, if we were to make it prettier, would the 1/2 go on the numerator?
It'd be a 2 in the denominator or a 1/2 in the numerator. She took that pretty well. All right. So this, we good, Caroline? Did I go slower? Okay. Arc sine x plus x times the square root of 1 minus x squared. So arc sine x, they're not even giving me a challenge. That's just the exact rule. Okay, so 1 over the square root of 1 minus x squared. What am I going to have to do on this one? Product rule. What am I supposed to be doing? Yeah. Okay, so I'm just going to move that now. I need to think of this. I got to use Michael's tip. Make that to the 1/2 when I'm thinking about it. Okay, so here we go. The first, what's the derivative of the second? Negative 2x. Oh, I'm running out of room. That was just first times the derivative of the second. I still need plus the second. Whoops. Times the derivative of the first. Okay. And that's the gross answer. It can actually be made very, very beautiful. But I'm low on time, so I'm not making things beautiful. I'm just taking derivatives. Okay? All right. Cosine inverse of e to the 2x. So I'll get my formulas ready. Okay. So this is the same as arc cosine. Okay. So you're just putting e to the 2x in instead of the x. And then you have to do times the derivative of e to the 2x. Okay. So f prime of x would be negative 1 over square root of 1 minus e to the 2x squared. Okay, so I just put e to the 2x instead of the x. And then I have to say times what? So the derivative of the 2x is e to the 2x times 2. Do not move any x's down. You're thinking of ln. Are you thinking of moving that to the front? Caroline, is that what you're thinking of? Oh, no. Yeah, that's different. So remember, if it's e to the something, it's just e to the something times the derivative of the exponent. So it's different. You're thinking like if it was x to the 2, then you bring the 2 to the front.
So why is it multiplies e to the 2 x multiplied
because to take the derivative, it's chain rule on e to the 2x.
Oh, sorry, it's going after the
Yeah, that's true. Okay, so my last problem. What's the problem with my last problem? Yeah, I got to do implicit because I got x's and y's on both sides. I can't isolate it. So it's going to be fairly disgusting. And don't even know if we'll finish, but we'll try. All right, so we'll give it a shot. If we don't, then you'll just know you won't be able to do the one at the end. It'll be fine. Okay, so ln of x plus y. It's just because there's algebra to get the dy dx by itself. And the algebra takes a while. Okay, so that's the same problem. I'm just rewriting it. Okay, so how do you take the derivative of ln? And then you have to say times the derivative of x plus y.
Which is 1 plus 2.
And then arctan, so lucky for me, there's the arctan rule. So I would do 1 over 1 plus, put the x over y in. And then what I have to do times the derivative of the x over y. So that's going to be a quotient rule. Okay? Six. Yes. So that was low d high minus high d low over low squared. Okay. So what we have to do is we have to multiply all this stuff out and get the dy dx's on one side and the other stuff on the other. I'm going to start just by going right here. Or, honestly, do you have any attention span left? Okay, so we're going to stop right here. We'll finish that, I promise, next class. This is the homework. They did number 41 wrong. You don't know how to do number 41 anyways. Well, you sort of do. But any of the ones that are implicit, I just didn't finish showing you how to isolate. So as long as they give you f of x and you want f prime of x, but we'll spend some time on it tomorrow. No. So inverse trig, I'd like these turned in separately, even though they're both from 15.3. So the log ones will be turned in as their own thing, and then the inverse trig things will be turned in as their own thing.
So we can do 20 or 40.
I don't know for sure. I didn't check to see how many of them were implicit. But if the y is not isolated, then you could have trouble, but you kind of know enough.
So we worked with this before. Yeah. So everything that we've just done for question today is one word.
Remember the Threads of Care coat drive begins tomorrow and lasts through next Wednesday. If you bring in a new or get renewed coat, it will be eligible for withdrawal day on December 18th. Donations will be accepted in the middle and high school.
December 18th. Makeup day. That's horrible. Great. Sorry.
Wait, what did that say?
That's a
You can have a pajama day on
I'll
December
take
18th, which is a makeup day.
so
Come on, Caroline.
Wait, so you said we
I
can
shouldn't have looked, but come on, y'all are smart kids. You would have figured it out.
so we can turn in this stuff.
That should be the lottery.
I tried so hard. Caroline, it's the thought. It can't catch everyone. It's the thought.
I mean, you're either going to donate a coat or you're not. So
Yeah, there
you're
is.
probably not going to go buy a coat just to get a pajama day.
No, we're doing a pajama day.
Caroline, they ever work out in having 2 hours per day?
We're having an entire week.
I actually tried
It's winter because Birds of Care did a pajama day.
See, this is why I don't ask you how many attention span left at the beginning of class. Because then everybody just told me to go in. And I couldn't do anything. A weight mask.
It might have been sent. It's not Mr. Fox. I posted that. And I do go to bed. I mean, I was not bad. Yes. I fail a lot. I sleep, and it wakes me up.
Oh, so much
Like
more
30
tired.
times a night.
You could try standing up though, when you feel sick. God, like you want out of here or something.
Or you stay packing up with me. You finish your
Name's like code word, get me out of here.
you have the hours. Every by the end of the semester, right?
That sounds right. At least one of them has to be at least
I did 1.5 hours.
or maybe it has to be 2 hours.
What else qualifies you? 4 hours.
It would be like if you tutored somebody, just like any adult
Literally anyone
would
else.
sign that you did it. Go!
But the rest of them
Are you still causing trouble over there?
No.
That's a rhetorical question.
No.
I'm not erasing
Huh? What do you mean? I tried to rewrite something, but then it didn't work out. I'm not trying again next month.
Hello. Hey, how's it going? Welcome. What are we working on? Corrections or packets?
I need to work on directions. Oh, no.
maybe
Okay. All right.
And are you just doing test corrections or you?
Yeah. I did the pickup one.
Which one's this one? There or there? There, got so much. Very good. She improved it. Short back and stuff. Y'all doing corrections there?
Let's not talk about that.
It's in the 30s. I guess I can.
Wait, so wait,
I probably know
wait,
in that.
yeah.
Yeah,
Really?
I basically just want to use for a long correction. So it's otherwise I'm a teacher. Yeah, there is that cabinet. Yeah, there is that.
She came up with she would get still,
Oh, dude. Hey, is this your secret channel? No, I thought it was. It was just-
So for this one, you're loaded and then just trig. Yeah. So do the R and then
I'm
from
not letting you
yes,
see that.
inverse tangent. So is it going to be square root 6 over negative square root 2?
That would be, yeah, I use very easily. It would be very easily.
You'll be perfectly on top of each other.
Alright. Okay. Not trying to.
Get like a pretty high strung test that might help me with the correction.
Alright.
Just like sit between them. That's probably best.
I mean, Rachel obviously got like the other one. Yeah, but I cannot help you on the last problem.
Oh, yeah, I can.
I can help
I got a whole one mark on that problem.
Same. I thought I did such a good job and I got one.
I knew I could, I pretty good. Yeah.
Well, no, I just like.
Let's fit the desk. Like how we have no walk-ins room. Like I feel like we can scoot each one back a little bit.